Okay, we are recording. We are recording. And we're looking at line integrals of vector fields. We're looking at an application of line integrals. So I'm going to go right to the reading in the book here. Look, here's figure 11. Okay, and what you see is a space curve that goes from point P sub 0 to P sub n in three-dimensional space. And picture that there's a vector field F acting in the three-dimensional space. So at every point along the space curve, the vector field, theoretically, let's say, helps the particle move along the space curve. Okay, it can hinder it too, but let's just for now assume that it helps it. So look at the point P sub I minus 1 and the point P sub I in figure 11. There's a piece of arc length there. And what we want to do is we want to figure out the piece, the work that the force field does in moving the particle along that little subarc from P sub I minus 1 to P sub I. So what you can do is you can, now I'm just looking at the book too to make sure I'm saying everything correctly. Yeah, you pick a point in that interval from P sub I minus 1 to P sub I, and you look at the vector, the force field vector. Well, the force field vector, as you see, points up, not completely vertical, but at an angle. But in regards to moving the particle from P sub I minus 1 to P sub I, it's that tangent vector that gives the direction, that gives the component of the force field vector that is used in doing the work to move the particle from P sub I minus 1 to P sub I. So if you take the dot product of the force field vector with that unit tangent vector, okay, you get an approximation of the work. But the approximation of the work is not going to be very good because that unit tangent vector can be much longer than the arc from P sub I minus 1 to P sub I. So what you do is you multiply the tangent vector, and that tangent vector, by the way, is at some time T sub I star. You multiply the tangent vector by the piece of arc length between P sub I minus 1 and P sub I. The idea is that that would be a logical scalar multiple to use. Now, obviously, if you sample more points along the space curve, then the tangent vector scaled by the arc length would be very accurate. Okay, and so the work done by the force field F in moving the particle from that point P sub I minus 1 to P sub I is approximately equal to that dot product. Okay, and we learned about dot product back in section 9.3. Okay, the work is equal to the dot product of two vectors. One is the force field vector, and the other is the the distance vector where the particle's actually moving. So we can re-express this dot product as the dot product of the force field with the tangent vector times delta S sub I. Well, okay, we would compute one of these quantities along every little piece of arc. Okay, so you know they take the entire path C and break it up into little pieces of arcs, little arc pieces. We would compute the work along each of those arcs, those little subarcs, and add them up, and you would get this. Well, what happens now is you have this summation, and obviously, as you let n go to infinity, the summation is going to equal a line integral with respect to arc length, and that will actually tell you the total work done. I'll highlight it here. That will give you the total work done. Hold on. Let's make it yellow. This here, this Riemann sum, would give you the total work done in moving the particle along that path C. But of course, it's an approximation. To get the exact work, you have to let n go to infinity. Well, when you let n go to infinity, you're going to get then Let me just highlight that. I want to explain it, make sure I'm explaining it accurately. The work would actually then be equal to a line integral with respect to arc length. So now the line integrals with respect to arc length that you learned come into play. Okay, that concept now has an application. So, but again, now, okay, we're integrating with respect to arc length ds, but we want to change we don't want to integrate with respect to arc length as the variable. We want to integrate with respect to time as the variable. So what you can do is you can take that dot product. Okay, you can take that integral, I should say, and the tangent vector, that unit tangent vector, is equal to r prime of t divided by the length of r prime of t. Okay, we know that, and they are writing the ds as the length of r prime of t dt. Now, how are they doing that? Let me show you. So let me go to the whiteboard here. So remember, if you remember, ds, when we talked about line integrals, we showed that ds is equal to the square root of dx dt squared plus dy dt squared dt. Well, what is this square root stand for? It is the length of the derivative vector of r of t. Now, incidentally, and therefore, ds, therefore, ds can be replaced with the length of r prime t, the length of that derivative vector dt, and that's what they're doing. That's what they're doing in that portion of the book that we looked at. And incidentally, it's no different. It's no different if you work with three-dimensional space, which the figure did. Okay, three-dimensional space. The ds just equals the square root of some of those squares dt. But this here, that square root, is just the length of r prime of t. So therefore, when we look here, okay, to the work formula, okay, we can abbreviate f, the vector field f, with, well, x, y, and z. Every point x, y, and z in the vector field f is a point that is on the space curve. And so the vector r of t, the vector function r of t, for different values of t, you will get those coordinates x, y, and z. And so we can basically replace then, since our variable's t now, we can replace that vector field f with respect to x, y, and z with r of t. And then the tangent vector is just r prime of t over the length of r prime of t. And then ds is equal to the length of r prime of t dt. And therefore, you get this integral. The integral from a to b of the vector field f evaluated at r of t dotted with r prime of t dt. the r prime of t's cancel out in the first integral. And so now, I mean, this is what we, where we wanted to be. The line integral of a vector field f along a space curve C is given by that integral. Now, you'll notice they abbreviate it. So let me show you where that comes from, because I want to get to an example here. No, go back. So they have this. This is that formula 13 in section 13.2. Quite beautiful, really. Okay, that's a dot product there. Okay, so this is shorthand notation. The integral of f dot dr is shorthand notation. Now, you know, here are the dots. So why does the integral on the right equal the integral on the left? Well, let me show you. Remember, if you were to do Leibniz notation, dr dt, that would get you r prime of t, right? So therefore, dr, that differential vector, equals r prime of t dt. So r prime of t dt can be denoted by dr, and the vector field f with over the its input is r of t, we can just write it as f. So there you go. So when you think of this, you think of work. When you see that line integral, that means find the work. Find the work that the vector field f does in moving the particle along the space curve C. That's what that means. So let's go ahead and do an example. I want to get an example done here, and we will take a break then, but let's get this example out of the way. Okay. Let me give you a moment to copy this example down. Are there any, are you comfortable with this idea? What I just explained about the line integral of a vector field? Maybe give me a thumbs up if it makes some sense. Okay, all right, Norina, and it's going to take a while to think through, but Norina and Arian are at least, and Alexander are at least initially comfortable. Simon too, wonderful, wonderful. Has anybody ever had to do this in a class where they had to find the work that a force field or vector field does in moving a particle along a path? Has anybody seen that in a class of theirs? Okay, maybe not yet. All right, all right. Let me give you a moment to copy the example down. Okay, so in this problem, what we want to do, okay, we want to find the work done by this force field in moving a particle along the quarter circle that starts at 1, 0 and ends at 0, 1. Okay, so of course, since we need to find work, we are looking to find the line integral for this vector field. And of course, we recognize what that means. Actually, one moment here. Once I have dt down, I have to put in t limits, a and b. So this is like abstract. This is just, you know, I don't want to say abstract, but it's the right-hand side. That's the concrete part, right? But it just means you're finding work. But to find the work, of course, you have t limits. So you have to parameterize this quarter circle. This space curve C, if we were to, for this space curve C, if we were to write out R of t, it's a quarter circle. So what would x be, and what would y be? All right, that's right, Lexi. X would be cosine of t, and what would y have to be? 1 cosine of t, because it has obviously radius 1. What would y equal? Good. That's right, Lexi. That would equal sine of t. So you can't do the problem unless you and what would t go from? What would t go from? What would the limits on t be? It's a quarter circle that starts at 1, 0. I mean, if I drew a little picture here. Yeah, let's see. It starts, here's x, here's y. Curve starts at 1, 0. I think you're right, Lexi. And it ends at 0, 1. So here's the space curve. Ooh, goes that way. Yep, I agree. T would go from 0 to pi over 2. So now you have everything you need to work this formula out and find the work. You have everything you need. Oh, I'll label this. This is the curve C, right? Okay, so let's go to the next page. Now, what I've done, incidentally, is I included this is actually example 7 we're looking at here. I included a figure 12 from example 7, and it shows, the space curve of interest moving in the direction it should be moving in. Starting point is 1, 0. Ending point is 0, 1. And what is being shown also are the force field vectors based off of the force field function, which has components x squared and negative xy. Now, how do they get those force field vectors? They used a program, and I'll just tell you, if you go to the MATLAB programs and look under section 13.2, there's a MATLAB program that will draw a force field on top of a space curve, and it actually reproduces this picture in figure 12. Okay, so if you go into MATLAB programs in Blackboard and go to section 13.2, the program should be there. It's the second program under section 13.2. That second program will produce this graph. And based on the force field vectors, okay, that you see, those black vectors in figure 12, and based on the space curve C, do you think the vector field is helping the particle move from the point 1, 0, the beginning point here, to the ending point 0, 1? Do you think the force field, the net effect of the force field is to help the particle move along that path or hinder the particle moving along that path? What do you think? Are the force field vectors acting against the movement of the particle or with the movement of the particle overall in figure 12? That's right, Narina. That's right, Logan. The force field vectors are working against the movement. That's right, Logan. That's right, Narina. Well, this means then, would the work end up being a positive value or a negative value? What do you think? Should the work be positive or negative for this problem? That's right, yeah, it would be negative because the force field is acting against the overall acting against the movement. Okay, and I guess just to be kind of complete here, I'll add this is r of t, right? That's my position vector, and as t varies, it moves, and the tip of the position vector here traces out that space curve. All right, so we go ahead now and we work out the problem. The t limits do indeed go from 0 to pi over 2. And remember I want to say this the right way. Well, cosine squared of t is x squared. Remember, for r of t, x is cosine of t. And then the other part of the force field, right, is negative x times y. So that would be negative cosine of t sine of t, because that's your x and that's your y. Okay, and then this is your, you see your derivative vector. Now you could write this like this if you wanted. You could write this as cosine squared of t, comma, negative cosine of t, sine of t, right? And you could dot it with negative sine of t, cosine of t. So I just chose to use the IJ notation, but how many like using the component notation? In the purple there. How many would maybe do it that way in their work? I'm sure some of you would. All right, Narina would, and that's fine. That's fine. Okay, Yeva switches back and forth. Okay, no problem. So we end up then getting this integral. And we note that the terms are like terms, cosine squared of t, sine of t, so we can combine them. Give me a thumbs up if you're good so far. When you're ready, I'll move to the next page. We have one more page here. Okay, wonderful. Looks like everybody's okay. Most everybody. I don't have everybody. Not everybody's replying, but it's pretty good portion. Pretty good reply. Okay, so here we go. Okay, so I think the pi over 2 got kind of, hold on here, I think I can just kind of, one moment. So this is, I knew I would, all right, top limit is pi over 2, right? That's fine. So I'm going to use substitution because cosine squared of t is just the same as cosine of t quantity squared. So let u equal the cosine of t. It's an easy substitution. And then du dt is negative sine of t. And it ends up that negative du is negative sine of t dt. So you now get a new integral with respect to u. The zero limit on the bottom, which is the t limit, well, since u is cosine of t, okay, since u is cosine of t, the cosine of 0 equals 1, right? And the top t limit was pi over 2, so the cosine of 90 degrees equals 0. And now it's just a an easy problem to do. You work it out, and you're going to get negative 2/3. So we did get negative work, and the work is negative because the force field impedes the movement of the particle overall. And it looks pretty definite here, but we can add the word overall, right? But I think, I'm thinking about your fourth exam, a problem like this. It would be how many, I mean, the graph of the force field on top of overlaid with the space curve, particularly for a two-dimensional force field. I think it's valuable to have the picture. And again, you have a MATLAB program that you can adjust it to produce a picture like that. it gives you an idea. Okay, well, I know my answer has to be, I mean, it won't always be clear, but sometimes it's very clear whether the answer should be positive or negative. How many might utilize the section 13.2 program, the second one, to draw the force field along with the space curve? Okay, Yeva says she might do that. Sure. And Norina would. Okay, wonderful, wonderful. It's nice when we can connect things, when we can connect. The illustrations really help you appreciate the material. And this book is very good, the Stewart textbook, because it has so many good illustrations. I mean, yes, you have to pay for the ebook, and of course, the online homework. We all appreciate that. You have to pay for the ebook, but I'm telling you, it's worth it. It's worth it. If it helps you understand, it's worth it. And book prices, you might notice, at least I've noticed, like particularly ebook prices, they've come down in recent years, or at least they're coming down at Montgomery College. So that's a good thing, right? We want our students to save money, but we like them also. I like my students, and I think most professors would like their students to have good learning materials, and this book is just so good. It's truly quite good. I mean, every page in the book has figures on it, um, helpful illustrative figures. Okay, are there any questions before I stop the recording? Give me a thumbs up if you're feeling good. Okay, Logan's good. Christopher's good. Yeva's good. Marina's good. Alexander's good. That's good. All right. All right. Well, let me go ahead and stop the recording here. Excellent.